Welcome! This video is a presentation of the Capstone project that I've done as part of the Advanced Data Science with IBM specialization on Coursera. It's a dataset that comes from the website Kaggle, which you certainly already know, and that is organizing a data science competition. So the data has been provided by the Los Alamos National Laboratory, and it's about earthquake prediction. So it's pretty exciting, and I hope you'll enjoy that. Let's get started. So let's talk first about the laboratory experiment. So we have two granular layers that are under a constant stress, and they are sheared in the middle at a constant velocity. And what will happen is that there will be cycles of stick and slip, and that mimics the cycle of loading and failure of tectonic faults. So the experiment is simpler than real fault in Earth, but it shares many physical characteristics with it. So from that experiment, an acoustic signal will be recorded using a piezoceramic sensor. An initial work has already been done on that topic, with a publication in 2017, and it showed that the prediction of this kind of laboratory earthquake is possible. The physics, if you are distant from a failure or if you are close to a failure, is different. Based on that observation, they took 100 statistical features, they fed that to a random forest model, and they were able to predict with a good accuracy the time to the next failure. This experiment has been done in the case of quasi-periodic cycles. For the competition, the team has provided a much more challenging dataset with more aperiodic failure. Okay, let's have a look at the files that are provided. First, we have train.csv, which contain our training data. It's one single file of continuous data experiment. There is only one feature, which is acoustic data, an integer, and we have one label, which is our time to failure. So there is a lot of observation, more than 600 million. Following that, we have a zip file, test.zip, that is containing more than 2,000 files. All those files are segments of 150,000 observations, and they are containing the feature only, the acoustic data. So that's the file that we will have to use to make our prediction. The last file is the sample submission.csv, and is a file that we have to use to enter the competition. There is two columns in this file. One that is the seg ID, the name of the file coming from the test.zip, and the second is our prediction, the time to failure for this segment of observation. Now, we will start to have a look into our data, beginning by the features, the acoustic data. I've computed statistics for both train and test sets, with the count, the mean, the standard deviation, the minimum, the maximum, the skewness and the kurtosis. I've also plotted the distribution of the values. The first comment we can make is that given the values that we have for the mean and the standard deviation, we have minimum and maximum values that are pretty far from that. Also, the kurtosis is very high, showing that we are in the case of a leptokurtic distribution. This is confirmed on the plot where we see that most of the values are tight around the mean, and we have those fat tails with this little bump at the very end. The second comment I would like to make is that there are some difference between the train and the test sets. The differences are not huge, but I think we can suspect that there is some kind of difference between the data that are provided for the train set and for the test sets. And I think it's important to keep that in mind. I've also computed statistics for the labels the time to failure, and I've plotted the distribution, which looks more like a folded distribution. Some of those values will be important to interpret the prediction of our model going forward. So let's take note of the mean, the standard deviation, and the maximum values. To go on, I've decided to plot a few samples. As the test set has been provided in a segment of 150,000 observation, I took the same scope and had a look at the training data. In blue, we have the absolute value of the acoustic data, and in red, we have the time to the next failure. So it's not obvious to find a relationship between the acoustic data and the value of the time to failure. We have here two examples. On the left, the time to failure is high, and on the right, it's very close to the failure, and there is nothing that spots the eyes that you can tell it's this one is close to failure, this one is not. What if we have a look at the segment just before failure, the segment while the failure is occurring, and the segment just after? And it's about the same. It's difficult and it's not obvious to find a pattern or an event which would help us to understand at what stage we are in the process. So let's take another approach and have a look at things from a higher point of view. So what I've plotted here is the whole training data set. I've taken the mean of the acoustic data and the time to failure for each segment contained in the training data set. At this level, it's pretty clear that there is a pattern. The acoustic data is increasing and increasing, leading to a higher peak, and after that it's decreasing, and then the failure occurs. But also, sometimes it can be a kind of false pattern, where the peak is less high than the other, and then the failure is not occurring after that. Now that we have noticed this interesting pattern in the train set, let's plot the test set to see if we can observe this behavior as well. And now it seems that the test set, when you take the segment sequentially one by one, doesn't look like what we have on the train set. It's time to clearly frame the problem, and before we try to give an answer, be sure that it's at the right question. There are two sets of assumptions we can make. A, the aim of the competition is to provide a prediction based on a segment of observation only and without knowledge of what happened prior to that segment, as it has been done in the initial work. What we have seen so far from the dataset in the data exploration tends to confirm that. B, as we suspect there is a temporal dependency between segments, we will try to extract value from that. Even if it doesn't seem to stick with the competition framework, it really seems to be an interesting path to explore. To answer our questions, I've worked on several models. I've evaluated them against the mean absolute error, and I've used for that a validation set taken out of our training data, the same for all model, of about 1,000 observations. I've also submit prediction made by those model to the Kaggle website and add a feedback on the performance also. We have to take we have to be careful with those results because it's only 13% of the test data that is used to calculate the metrics, so it's about 300 and something observations. Also, I have plotted the prediction of our models against the ground truth or label that we have in the validation set. The first model, in fact, the model number 0, is just a naive prediction using the mean on the training set. So it's just to give us a baseline to interpret the result with our model afterward. We have then 3 models in our A case, where we are trying to predict the time to failure based on a segment only. And I've used the random forest as in the initial work, and also MLP and a recurrent neural network, with a gradual improvement in the validation and almost on the test set. The last model is a model where we are trying to answer the question of the B case, and it's a recurrent neural network. And we see that using the temporal dependency between segments, we have a great improvement in the performance. And we can see also on the plot of the prediction versus the label, the target, that we have an answer that is smoother than what we've got with the previous model. But when we submit the prediction from this model to the Kaggle website, then it's pretty clear that the test set doesn't allow us to do that. So it's a dead end. Okay, so we have entered the competition with, I would say, a decent entry in the leaderboard. We are somewhere in the middle. So what's next? In competition like Kaggle, till you have not reached the deadline, then there is always room to improve what you've done. And there are several ways we could improve the work that have been done so far. The first way to improve our model could be data augmentation, because we have been very careful so far with overfitting, but we could take some risk and build more segments with some overlapping, so we could have more data for our model to learn. Also, for our neural network, we could use folding to extract all the value from the training set, because today we have a validation set that is not used for training. Another way to improve our work could be to create ensemble of different models and see if we can get the best of our different models. The third way that I can think about to improve our models is based on an intuition. When I see how our models behaves, I feel that they are able to tell us if we are close or far from the failure, but not really the time to the next failure. So maybe our model would learn better if we were giving them this target to give us a ratio, are we close or far to the failure. Lastly, we could try other kind of algorithm. I'm thinking of LGB and XGBoost, which are the superstar of the Kaggle website because they are very efficient on small dataset. And also I'm thinking about a convolutional neural network that can be used in the case of time series. First, I'd like to have a few words about the methodology. I've followed the lightweight IBM Cloud Garage method, and I have to say that the process was not linear at all. I've started with data exploration, then moved to ETL, but as ETL made it very easy to access to the data, then I went back to data exploration. From that, I went to features engineering, and then to model definition, and I've used the model to refine the features, and I made some feature selection at this stage. So I went back to the feature engineering, went back to the model again, and then I had a few loops on different kind of model, and then I had to create some more feature because I went to the idea to have a recurrent neural network, and I needed to break down the data in windows inside the segment. And from that, only I went to the final product that is, in my case, prediction for entering the Kaggle competition. About architectural choices, the first thing I have to say is that the detail of the choices made has been written down in a document called Architectural Decisions document. So if you want to know the details, then you can have a look at this document. The most important choice have been for me to use Jupyter notebooks on the IBM platform, because it was for me the more efficient way to work, because it's well-known tools. Also, I've used Apache Spark and Parquet files to access the data, and it was of great help due to the large quantity of raw in the files. And last, I've chosen to use different framework for the model definition, and I've used Spark ML for the first models that I've done that are random forest, because it was out of the box in Spark ML. And after that, I've used the Keras for the multi-layer perceptron, because I've tried to stick as close as possible to Spark, and I know that from Keras you can export a model in system ML, and then you can still work in Spark. And at the end, working on the recurrent neural network, I've used PyTorch, because it's more flexible for me when you have to deal with this kind of network, and also because it's a framework that I know the best. Let's talk a bit about data pre-processing and features engineering. As in the initial work, I've computed a few statistical features. It's often a good way to extract representative values from a large quantity of data. But as we are in the case of a time series, I wanted also to try to translate from the time domain to the frequency domain, and I will focus more on that because it was interesting to do that inside Spark. So at the ETL stage, what I've done is I had this very long file of acoustic data. So I broke down the file logically into segments by adding a segment ID to make groups of 150,000 observations. And from that, I was able to reduce and create dense vector of all the observation for a segment ID. So this way, I've created data that was ready to use for MLlib transform. So in MLlib, there is no Fourier transform, but there is a DCT, which is a discrete cosine transform. It's the real part of the Fourier transform, so the cosine part, and I use that, and it worked well. So the last step was to summarize the data into bins. This way, I really shrink the data, and it was ready to be consumed by the models. The first model I've built is a random forest, as in the initial work, and I've also used that to have a feedback on the feature's importance. You can see on the histogram that we have in orange our statistical features and in blue our frequency features. So the model gave a lot of importance to all the statistics that were the very high or very low percentile. And on the frequency side, it was more on a specific range where the feature seems to be more important. So next, I've recreated features more focused on the statistical features that was important for the random forest model, and also I've recreated features that were more focusing on the frequency range between 50 and 75. Next, I've made a grid search on different combination of feature set to see what was performing the best. So the best performance was achieved by using the frequency range. So that's what I've kept for the other models. About models definition, I won't go too much in detail about that. I think I've already spoke about all the logic that I followed on that. And if you want to have more details, then you can have a look at the notebooks that are available on my GitHub. So it's a very, I would say, classical way of doing hyperparameter tuning. About evaluation, I've used mainly mean absolute error because it's easy to interpret, and it penalizes the model less on a great error, and my intuition was that it was a great idea to use that because of those peaks in the time to failure. And lastly, it's what is used in the competition, so it was a way to stay consistent. And the second thing I've used is to plot simply the prediction versus the label and see the results. To conclude, I would like to say that the topic was motivating. It was also challenging to enter a competition on Kaggle, and finally it was of great help and interest to use Apache Spark on the IBM Watson Studio. So I would like to thank IBM that gave me access to those resources, the Kaggle website and community, and the Los Alamos National Laboratory for the datasets. Also, I would like to thank whoever has watched this video. I hope it was interesting. Have a good one, and bye!